Ready?
I think so.
Thank you guys for having me. For those that don't know me, I'm Jim Cornett. I'm a hydrogeologist, which means I know a lot about dirt and water. I like to use big words because it makes me look important. And so I like to keep things loosey-goosey and I get all excited and jump around and stuff. And so as we go through this, one, forget the frog in my throat. I'm drinking a little water. But if I say something you don't understand, stop me, please. Because I have fun with this. And so Chris had asked if I take up about an hour of your time. I don't know if I need to abbreviate that or not. Are we still good with an hour? I mean, because I want to talk about three big things here. And so I can keep it as short and succinct, but I do have 45 slides. And so I can click through quick or not. So we'll just go. Everybody good?
Good.
Excellent. All right, so I am Southeastern North Carolina native to the core. You guys can probably hear some of the grits flying out of my mouth. I can't help it. I grew up on Upper Cook Island. I had been in Southeastern North Carolina. I did all my undergraduate and graduate work at UNC Wonderful. Practiced out of Hampstead. We're a fairly small firm, about 25 guys, but as scientists, we work hard with McKim and Creed and other engineering firms to help quantify some of this science stuff and try to bring sense and not just bring bookwork to the equation. Does that make sense? All right. So, I'm going to do my best to not just read slides as we go through here. But so why we want to talk about a few things. Number one, why is there fresh water under ball heads? Where does it come from? Why is it so important? We're surrounded by salt water. Why is this water even here? What are the threats to the resource? How can we protect it? And then we want to balance aquifer recharge to stormwater. We're going to talk about that a little bit. So here's my big three. We're going to talk about potable water resources, the aquifer system, and also a little bit of what's coming in from the Brunswick County water line under the Cape Fear. We're going to talk about wastewater recycling. And we're going to talk about storm event recharge and flooding. And I know that's something that's near and dear to your hearts also, because where do the pumps go? How are we going to get rid of this, and how are we going to actually help protect critical infrastructure and properties? Part of that. So freshwater resource under an island. That's kind of weird, isn't it, to think that there's fresh water beneath us here. And so what I'd like to do is get you guys, I'm going to bring you on board as junior hydrogeologist here. And I want you to understand how the island itself, the microcosm of Bald Head Island, works. So we've got Cape Fear River to the west, we have Atlantic Ocean to the east. And what Jim has done is I jumped in the middle of the island, I drew a great big line, and I slid it to the side, and we crawled down in there. And so that's what we're looking at. So the superficial aquifer is about 40 feet thick. And what I mean by that, that's an unconfined water table. So it's recharged by rain. And also the water that's part of the irrigation and the water reuse for the club. There is a layer of clay that's at about 40 feet deep beneath the island. It's continuous. We have drilled countless holes around the island and actually collected soil samples and collected water samples, but water supply wells. So by the way, I've been out here since 2002. Counted countless water soil samples, and we're able to interpret, actually connect the dots with a lot of this stuff and come up with this semi-confined aquifer from about 44 to 70 feet deep. So there's actually fresh water all the way down to here. So the semi-confined aquifer is where we actually take our water supply from out here. And so it's protected by the clay beneath, which is just above the Castle Hayne limestone aquifer. But then there are saltwater mixing on both sides of the Trask. Does everyone understand that? Mm-hmm. All right, so first we need to think about density. Salt water is heavier than fresh water. Fresh water is lighter than salt water, which means fresh water floats. And so we actually have a bubble of fresh water, if you will, beneath the island. that is bound on the sides by salt water and actually underneath by salt water in the Castle Hayne Aquifer. So the primary resource of water is the intermediate aquifer. And so the island uses about 88 million gallons per year pumped out of the aquifer, then it's taken to the treatment plant. Once it goes to treatment plant, it's treated using membrane filtration and then sanitized and then mixed with the water that comes from Brunswick County during peak times when you need it, then distributed to the islanders. The membrane treatment generates mineral concentrate reject water. That mineral concentrate we actually put through a second RO to preserve as much volume as possible. And then the mineral concentrate actually flows out down a water line and is discharged through the bulkhead at the entrance to the marina down here. And so we double treat it to squeeze and keep as much water as possible. That's actually a picture of one of your well houses. So if you see these little green houses around the island, that's where your water supply wells are. So what are the threats of this resource? When you think about saltwater intrusion around the edges, when you think about on-island fertilizers, pesticides, because remember the island is made of sand. So anything that gets poured out, dumped, spilled, accidentally released will percolate downward and impact your water resource. Petroleum, hydraulic fluid, diesel fuel, gasoline, accidents, tanks, contractors, any of these can impact. And when we're talking about dealing with these on a part per billion contaminant level, it takes very little to actually contaminate your water resource. So as sensitive as our happy little bubble is, we have to protect it. So how do we balance the aquifer recharge versus flooding? Because your aquifer recharge is super important. Without rainfall, storm events, you would deplete your water resource and you wouldn't have it anymore. So Jim is a proponent for hurricanes because of the health that it brings to your aquifer system. All right, so what you're looking at, this is what the water body looks like beneath Bald Head Island. And so if you know how to read a contour, there's actually a hill, a mound of fresh water here. Then you get out under the conservation area, it's lower, and there's a hill of groundwater as you're going down towards the cape or the point itself. That hill of water naturally is at about 4 feet above sea level here and up to about 6 feet above sea level here. And so this is in a natural non-pumping state. That's what it looks like. And what can I do with that? That map is super important for me because I see where the water is under the most pressure, but I can also predict where it's going to flood. And those arrows are perpendicular to those contour intervals. So I know if I need to pump water, obtain water, get access to water, I know where it's coming from and I know where it's going. And that allows me to predict potential contamination, allows me to predict and protect the volume that's there, and allows me to see and understand potential saltwater influence around the island. The one thing that this doesn't show, but it's very important, is I know there's salt water to here. I know there's salt water to here, but I also know from test wells, and Chris can substantiate this, there's a flow of fresh water that comes off the island right here. That's the reason that is low. So there's potentially a high permeability or gravity coarse grained sand layer that's allowing the island to drain right under the conservation area out to the south. An area that I'm concerned with and I watch is West Beach. And the reason I watch West Beach is because of active erosion. And your first fancy term of the day is called angle of repose. An angle of repose is the natural angle that something will erode to. And so sand erosion is going to be very flat. Rock's going to be straight up and down. So when the Corps of Engineers in their infinite wisdom comes out and dredges, get a very steep angle of repose, it erodes back, and then you start losing lots on West Beach. Anyone ever seen that, or is there history here where people can remember who are losing lots on West Beach? That's where your most saltwater influence is, on the west side of it. So it makes me happy that we are beneficially reusing the wastewater on the west side of the island to help keep that saltwater at bay. So it naturally works just by mounting up the wastewater for the golf course on this side. So your current potable well locations in the island, we have about 16 wells. All of these wells are generally less than 60 feet deep and sealed in that intermediate aquifer. 4 were built recently, about 10 years or so ago. We drilled 4 wells in the conservation area, and we still have 1 well that is approved by the state that we can install. We just haven't done that or haven't needed it yet. So we have to head scratch now. What are we going to do for build out? Will we have enough water? So currently producing around 88 million gallons a year. The island build out is at approximately 63%. We talked about it a minute ago. So we'll need an approximately additional 62 million gallons of water here. Where is the water coming from? We have a plan. JP and I do. We're going to maximize the existing water supply wells. Unfortunately, water wells are seen and forget for a lot of people. And historically, through the original construction until today, you guys never had a very viable development. What that means is some of your wells are not producing like they should. So instead of just drilling new wells, what we're doing is we're actually going through and we're going to take your first 6 water supply wells. We're going to pull the pumps. We're going to video the wells. We're going to look at the well screens that are in the bottom. We're going to look at the casings that are in the bottom. We're going to evaluate the pumps. We're going to go back with heavy brushes, and we're going to lower the pH in the wells and actually clean and develop the screens so that we can take all of the old clogging, flow restricting mineral buildup out of the well. So essentially, we're going to rehab your detention well. Instead of a well just being dry, heck no, we're going to fix it wherever we can. We're going to understand what that is. And as we work through these 16 water supply wells, we'll be able to test to know how many gallons per minute, per day, per year each one of these wells will produce. So we'll be able to take those numbers and actually inject them into the equation to realize as much of the additional 66 million gallons as we need without doing new construction. Which is cool. That's an extremely efficient way to increase the flow without increasing physical bills. So now I want you guys to think of a crazy concept. Water is a conveyor belt, a literal conveyor belt, because we will take the water out of the ground, we treat it, and then we take that water and it comes through our homes and it takes all of our waste products out of our home. Toilets, sinks, whatever. And then it all goes back to the wastewater treatment plant, where we take all of the contaminants now out of that water and have a reusable drop of water. We don't want to drink it because it's not really palatable to think about doing that. But if you have a clean drop of water, you contaminate it and you take it over here and you take all the contaminants off, you really have a clean drop of water again. So think about water as a conveyor belt. All right, that's really all it is. Water is a conveyor belt, whether it's taking the waste out of our bodies, flushing it, whether it's taking waste out of our sinks, water is a conveyor belt. Because Bald Head Island has got this happy little bubble of water on it, this has been my big deal. Don't waste a drop. That's the reason JP is on top of every leak as quickly as possible with the potable stuff. That's the reason we double treated the reverse osmosis discharge water, so we can preserve as much as possible. I think Tony and I talking coming over here, the peak discharge is like 15,000 gallons per day, which is good for the concentrate. So we're preserving and keeping as much as possible on the island. All right, to talk briefly about wastewater. Water is not compressible. It's not elastic. And so it just is, it's a mass. And so as part of this, if you put too much water in a spot, you get a flood. If you take too much water out, now you got a drought, right? And we've worked really hard over the last couple of decades to track the water in the island. And so we take all the water that has the contaminants, take it through the treatment plant, and then the club actually uses irrigation or uses the highly treated water as a beneficial reuse irrigation. So we discharge into 2 ponds where it reassimilates into the ground. We also spray it on top to irrigate the golf course. And again, all of that is on the western side of the island, which in turn helps us with our saltwater intrusion issues also on West Beach. So we really have a balance going on here. Paul's Island is such a dynamic, happy little microcosm here. About 4.5 or 5 years ago, we were hired to put together an island-wide hydrogeologic model. And so we measured with help and cooperation with the Conservancy, measured and put together a physical groundwater contour map of the island. This does not have computers involved. McKim & Creed helped us survey and get tight, close, accurate elevations and locations. We took measurements over a period of time and came up with a working, empirically measured groundwater contour map. And so because we had this empirically measured, we were able to actually go back and create a model to help predict future hydraulic impacts. What are those impacts? What does that mean? The model gives us a tool for making stormwater management control, protect pipe infrastructure, protect personal property, where the pump's going to go. It allows us to predict most effectiveness of that. Where do we put our wells? We know where the water is thickest. We know where the water is flowing. We know where the water is contaminated, could risk downhill water supply. Wastewater management, because we're mounting up on the west side of the island, we're working with saltwater. And working with keeping the club's golf course really cool, because your golf course is the diamond of the island. You know, there's so many people that come here just for the golf course. We're able to use our own resources, keep it pretty clean and lush. All right, so we put together a computer simulation. That's what a model is. And so we built a computer simulation that uses geologic properties, weather and precipitation, evapotranspiration. Evapotranspiration is my second big word for the day, and that's actually saying how much water do the plants take up. So as things rain and get into the ground, where does it go? How much comes out and just goes straight up through evaporation? And then ocean and river influences around the island. So our ground model is really the world's most sophisticated sandbox. So back to this, you're looking at the water that's coming in from the top, the water that's coming in from the sides and the bottom, and then use and recirculating that water in the island itself. I want to ask us, what about Middle Island? You guys not include Middle Island in it? Nope, we did not. The reason we didn't include Middle Island is too hydraulically isolated. We had the main bulk of the island, but Middle Island over here is separated by Bald Creek. And so it really didn't make sense to try to incorporate Middle Island because any water that falls out here would stay out here. And so this is the model itself, anywhere within the yellow hatched or the yellow dotted line. We took the data points that we had, the measurements that we had, the interpretations that we had, and we put together this model. We also took a lot of the information the Conservancy provided. We worked with Dr. Paul Hardy back in 2000. When was that, Chris? Do you remember? 2009, something like that. We're able to actually create a three-dimensional flow model. What you're looking at here is, remember my analogy earlier of being able to jump down to the island and draw a big knife across it, slide it apart? Well, we can do that now. And this is an accurate depiction of the superficial aquifer that we talked about, semi-confining unit, that clay, the semi-confined aquifer where all your water comes from, and the model base, which is the clay that's just above the Castle Hang aquifer. And so I can now load this model hydraulically. I can put 30 inches of rainfall on it, and I can predict what the water table is going to do. I can predict where the flooding is going to be. I can predict where the water supply wells are going to withdraw and impact. And that was a part with a lot of the swale marshes in the conservation area, because folks were worried that if we put the water supply wells in there, we might impact the groundwater table. I was able to make all these predictions based on this model, whether it would or would not. All right, so to give you an example, this is the actual model groundwater table. This is the computer printout of all the contours. And how do we know that this is accurate? Does it match reality? If you'll notice, we superimposed our empirically measured contour lines, and they matched. So I feel confident that our simulations match reality. And we did a fancy statistical analysis to make sure that our error was as low as possible, because you can never make a computer model exactly match site conditions, but you minimize your error. You get it as close as possible to reality. And we're able to actually get this model to less than 6%, which is very, very efficient, very effective, and very accurate in model. All right, so we produced a calibrated groundwater model based on existing monitoring well measurements. Our model has the ability to simulate new drains or pond interconnections. Are we going to connect the ponds to help drain the island during a storm? Where are we going to put our pumps if we need to throw this stuff overboard? So stormwater management. Is the island a bathtub or something else? And that's an important analogy for me, because if you have a cup and it rains in the cup a lot, the cup gets full. And that's flooding. However, we're not a cup. So groundwater is present everywhere under the ice. Rainfall percolates downwards. Usually about 85% of what rainfalls percolates downwards because of the Jacobs Ridge and the other ridges in the island. And the greenness of the island doesn't allow a lot of overboard discharge of water. So whatever falls on the island stays on the island. And so as it percolates down, it now mounds up with the groundwater, because the rainfalls can be a lot faster than the water can flow sideways. The sand is approximately 75% sand and 25% air. So 1 inch of rain equals about 3 inches of water table rise. It's about a 3-to-1 ratio. And so 6 inches of rainfall is approximately 18 inches of groundwater table rise. And that was part of the issue this past September when you guys were having all your flooding and stuff. Because we got, what was it, JP, 20 inches of rain? Is that what it was? Which equates to about 5 to 6 feet of water table rise when all this rain hit. I can't remember where we got that photograph of what they were doing up here. Someone put it. Some of the PSO guys, I think. All right, so I'm gonna take a minute and erase this drawing because I don't like it. I want you guys to understand the importance of water table rise. Now, I'm getting ready to vertically exaggerate some of this. Here is the surface called Head Island. There's Jacob's Ridge and there's some of the ponds. We go back over and down. And under the island, and that natural mound of groundwater we talked about. Everybody see that? This is surrounded by salt water and salt water and salt water. All right, there's a basic engineering principle called friction loss. And friction loss means if you're trying to push water through a pipe, the water is flowing through the pipe, it's sticky on the inside of the pipe, that's bumping against the sides. And so the more friction loss you need, the more pump or more head or more pressure you need. You guys understand friction loss because you take a garden hose, put your thumb over the end of the garden hose, you get more pressure, but you get less flow, right? So that pressure is the mound of groundwater coming up. That restriction is the flow. So friction loss is your thumb. Well, if water goes through the sand, sand acts as a back pressure to hold it back. So you do get this mound up on top. You guys have seen this on the table. When you put a drop of water on it, you actually have a meniscus water that stands up. That's because of surface tension of the water. So the water can be sticky, if you will, as it's going through the sand, the superficial and the intermediate aquifer. So if we get lots of rainfall, it's not that the low points in the island fill up. The water table actually comes up. That. And so the flooding you're seeing is not ponding, it's not puddling. You're actually seeing an island-wide rise of the water table beneath the island. And the low areas are now windows into that water table. So you're not looking at puddles, you're looking at the entire island has flooded from beneath because of that 3-to-1 ratio. So if you have a foot or 3 feet, let's do 10 inches. If you have 10 inches to the water table, it rains 4 inches, now you got a flood. Not because it's sitting on top, but because it's filled up from underneath. Everybody understand that? It's a very important concept. So windows. It's not a bathtub. You're looking at windows into the natural groundwater table. All right, so we took our model. We thought about Hurricane Florence. We added about 30 inches of rainfall to the island. Model of hurricane. Action slides. We added 30 inches of rainfall to the island over a period of 2 days. So we went from stable and happy, great big mounds of water under the island. Some of these actually simulated it went from 6 feet to 14 feet in elevation. Because it filled up at a 3-to-1 ratio from beneath. You guys see the difference? All right, this is what I like because I like crayons. The yellows are above the ground surface. The oranges are really above the ground surface at about up to 4 feet, and the reds are greater than 6 feet. Let me clarify, in elevation, not above the surface. So we actually took the topography of the island and simulated the topography of a flood event, and what the water table would do to the island. So this is what it looked like, where it took the water table and actually went above the ground surface. Because it just filled it up. That's all it did. It didn't flow, it didn't concentrate. It's like a sponge, it just filled it up. So Chris McCall had asked us to, okay, we put in these pumps. These pumps are pumping between 3,000 and 3,500 gallons per minute. And these, the green areas represent where the pumps are generally put in the perimetering ponds. So we simulated pumping these ponds at 3,000 to 3,500 gallons per minute. And so there's before the pumps. We turned the pumps on, the emergency outfalls, and we waited for 7 days to see how the model would run. And so it actually showed that the water table across the island had dropped fairly significantly after a week. So here is what it looked like after a week. So if we do a comparison, see, the yellows have diminished, the reds have diminished or gone away, and the oranges have diminished significantly. I want you guys to look at something. Very little change in where the outfalls were. The change is natural. It wasn't from your pumps. The ability of the water to flow sideways is there naturally. It didn't drain just here and here. Look at this orange spot here. It's gone over here. All of this drained by itself in a week's time. And after 3 weeks, your flooding was gone. Natural, not by those two pumps. Very important point here. So, conceptualizing Hurricane Florence groundwater impacts, Hurricane Florence Task Force estimated approximately 2 billion gallons of rainfall on board Bald Head Island. So we have 2 billion extra gallons of water moving through the groundwater system. To give you just a comparison, Super Walmart can hold about 27 million gallons. Volume of water being removed from 75 Super Walmarts would take 2 emergency pumps, which is what you have, running at 3,400 gallons per minute for 24 hours a day. For how long to remove that water? Those 2 pumps running. Any ideas? 204 days to get that. And so the flooding went down, your pumps ran, but the pumps didn't do it. It did it by itself because of the sand. So why is that important? We do a flooding predictive analysis. We need to think about localized floodwater pumping and critical property protections. In other words, use your pumps where the most risk is. Are you getting flooding next to public works? Are you getting flooding at some apartments out on West Beach and South Beach? Use your pumps to minimize initial emergency risk, because you can temporarily lower the water table in a smaller area with those pumps. For your potable water resource management, the model can allow you to predict where you put wells and how the wells impact the aquifer that's there. Again, this is a tool that you guys have in your toolbox, it's small. Wastewater recycling, they're talking about deepening the Cape Fear River channel. How is that going to affect West Beach? I pushed really hard. A good friend of mine was in charge of all of the dredging for the U.S. Army Corps of Engineers, and I pushed hard for them to go to Jaybird Shoals. Does everyone know what Jaybird Shoals is? Does anyone know what Jaybird Shoals is made out of? Why is it there? It's made out of rock. It's a big limestone layer. And the reason that the Cape Fear River jogs to the east is it's going around that limestone. And I pushed hard for Jaybird Shoals to be drilled and dynamited so that the channel would be stable and it would protect West Beach. But it's cheaper money just to dredge than something. But long-term solution would be to actually go through the middle of Jaybird Shoals. All right, so here are your big takeaways. Number one, Jim loves hurricanes. Large rainfall events are absolutely critical to the health of your aquifer system. That's where the water comes from that recharges your aquifers. Number two, the teeter-totter balance of water reuse on the western part of the island, hypercritical. Number one, for keeping the jewel of the island happy and green, but number two, to help with saltwater intrusion, especially with continued erosive forces and dredging by the Corps of Engineers in the mouth of Cape Fear. Keep an eye out and watch when these guys start to put out plans for dredging the river because of angle of returns. That's something you guys just have to watch. I'm not plugged into that. Number three, Mother Nature helped drain the island faster than any pumping system. Be a little patient with the puddles, folks, please, because it will self-correct to a large degree. Use your pumps for critical needs. Use your pumps to help with immediate risk. Spending lots of money on pumps and lots of money on diesel fuel will help around the edges some, but the island will take care of itself. Why? Because it's safe, which allows a lot of water to drain off. All right. Did that in half a minute. Does have any questions? Yes, sir.
So just so you know, we have another item further down, and it's a discussion of private pumping. What we ran into in the last flood was individuals with low houses. I want to pump my own property. You know, you see the island pumping going on, but now somebody wants to stick a pump at their house, and they're just pumping it somewhere. And so the question comes down to, your water table's up, that area is flooded. The pumping you do at that a small pump or a private individual.
It'll make them feel better.
Well, that's the question. So it's not gonna, the question is whether it has any impact at all.
If there's an imminent risk and you can pump enough out rapidly enough to make a difference, sure. I mean, because that's an emergency. If you've got something that's going to people's houses, but it's coming from the behind Jacobs Ridge area, it'll make them feel better, but it really won't do anything.
Okay.
So, yes, ma'am. Do you have a question?
Well, I was just trying to piggyback off what he said. So, correct me if I'm wrong, but that private pumping is going to go somewhere, which is going to impact somebody else, right?
Maybe or maybe not, because if they're pumping with one of these little submersible pumps at 10 or 15 gallons a minute.
Yeah.
It's not,
It's not gonna make any difference.
it doesn't. It won't-
Doesn't help them and doesn't
you don't-
hurt somebody else.
You don't, there's no significant impact to the hydrologic cycle at all. They can put that pump in here out in the Katy River and turn it on and pump it on the island, hopefully get the tide to drop.
Mhm.
It's negligible, it really doesn't matter.
Another thing that happened or do, so we try and get the water off the island. So you're basically taking water out of, well, trying to lower the water table by taking water off the island. At one point, there was a question because the club had their sprinkler system on. And so I'm looking at, okay, we're taking lagoon water out and we're spreading it across a bigger area. Can you talk to that a little bit?
Help clarify the scenario.
Well, the scenario is that the lagoons are high. The island is flooding, lagoons are high.
Yes.
And now we got our sprinkler system on the golf course going.
Yes.
And now I'm dissipating that water from the lagoons, which are holding the water or reflecting where the water table is. And I'm spreading that out over a much larger surface.
So are they pumping out of the lagoons on the golf course?
Well, they were, yeah.
The lagoon water feeds an irrigation pond from which the irrigation
It's
system.
reuse water.
Yes, that's what it is. Yeah, I'm sorry.
It doesn't matter. That won't affect anything because that's water that's already in Lagoon 1. And so they're pumping out of Lagoon 1, spraying it on. All that's doing is helping keep the salt water at bay on West Beach. And so that water balance is still there. They might pump down Lagoon 1 some. But JP, do you know what the fluctuation is in the water table in Lagoon 1 when they're running it? Does it have a significant?
And we have numbers, so we can see, like, say for the week that we pumped during the PTCA, it took us X amount of days to get 16 and 17 down to a certain point. That helped us at the wastewater plant, so that was a critical need. But other than that, we saw water just redistribute itself along on the island.
So what, you'll get essentially interstream divides. And so you have a water table. You have a golf course. And you pump the window in the superficial aquifer of pond 1 down, which will induce flow from the sides into pond 1, because pond 1 is not lined. It isn't lined, is it?
Now, two of them are rapid infiltration ponds. So.
Oh, yeah,
water
3
goes down, it comes up.
Oh, yeah, yeah, actually, Tony and I modeled all that stuff. And so it redistributes the mass, but it doesn't get rid of the mass. And so if there's flooding around pond 1, it would help by temporarily dropping the water table. The minute you turn those pumps off, that water table is just gonna pop back up. There will be some drop in it, but it wouldn't be huge.
Those are the two pumps that we put go to the ocean outflows.
I got you. So those, what you're doing, so what, if you're pumping the outflows, it will help draw the water table down
Right.
some. Let's go back. All right, so where you're pumping here and around the edge there, it will help drop the water table down, which very, very regionally will cause water to flow to the aquifer quicker. But it's still not a huge impact. And I know that just because look how well the conservation area and the eastern side of the island rebounded by themselves. I mean, look at here in the middle of the island, how red, orange, and yellow it is. And over here, it's gone. And over here, it's gone. Why? Gravity and flow. So does it help?
That area that drains, you said that you're just pointing at?
Yeah, well, this, you can actually see in the conservation area here, this area right here naturally drains to the south. And we know that because we have test wells in this area. And those test wells are just as fresh as they can be, fresh water. And so we don't know exactly why it does. I just know that it does. And the only way that would really happen is if we had a higher permeability a coarser grain sand, gravity sand, shelly bed, something like that, that's causing that drain in the center of the island to the south.
You touched on something there. As you're doing that, as you're describing this, I know you're describing all these things as happening instantaneously, and they don't, right? I mean, the rain takes some amount of time to go through. And
There's
the
7 days.
Yeah. Are there parts of the island that are, because of the soil composition or something else, more or less permeable than others? Or do y'all look at that at all?
Yes, well, the eastern end of the island, the center part of the island is the most permeable underneath Burley Conservancy. And there are a bunch of marshes out there, swale marshes, and these inner dune marshes are actually windows into the groundwater table because the groundwater is touching the bottom of the topography out there.
Yep.
But that is the most highly drained area on the island naturally. And so it drains the center of the island is the most permeable. The eastern is the second and the western is the third most permeable, with the exception of right along West Beach, and that's just because of erosion from the channel deep. Answer your question? There we go.
So Jim, one of the questions we had coming out of Tropical Storm 8 was, do we enlarge the size of the pump, the emergency pump outfalls on 17 and 8? And enlarge the pipes to move more of that stormwater off the island more quickly?
And it still has to migrate from the center of the island out to here, and that's gonna take weeks to get there.
Well, I mean,
But-
the
well,
lagoons are full. The lagoons are, yeah, I mean, the deal is the lagoons are full. They're overflowed their banks.
Yep.
They're underneath people's homes.
Yep.
And we're trying to get that water out from underneath there, and roadways are flooded. So only actual emergency vehicles can get through them. So the idea is to try to lower the floodwaters as quickly as we can in the most prone areas. The emergency, the bypass lagoon and the gravity flow out falling back is only going to move so much water. So what do you do with the rest of it? I hear what you're saying. I've learned a lot today about how much nature is what drives most of the drainage and the absorption into the water table. But for that period of a 1 week or 2 weeks, or in the case of Florence, 3 weeks, you had pad mounted transformers underwater. Power couldn't come on till the floodwaters receded. And in the meantime, we had mold that destroyed hundreds of homes on the island.
Understood.
So what can we do to prevent that from happening again?
Subjectively identify where those trouble areas are, and that goes back to using it for critical need infrastructure.
Mhm.
And withdraw water from those points, but it's got to go all the way to the outside of the island. And so it's got to go over Jacob's Ridge, or it's got to go into Bald Head Creek there, one of the two.
Let me try this again. The damage to the hundreds of homes was all over the island because all of the electrical infrastructure was off.
And you can see that.
Right.
Look at the island-wide flooding from Florence.
Yeah. And so it's all emergency flood prone and critical. So to me, what else can we do to remove as much flood water as we can off the island when you have 30 or 40 inches of rain? I mean, the water table is going to do just fine. But in the meantime, we're trying to prevent damage to property.
Understood. Without respect to money, it would take a lot. To get it off in 30 days, would take 70 of those pumps. That's the quick math. And so you would have to have 70 pumps pumping at 3,000 gallons per minute to get that dropped inside of 30 days.
And off the island,
Off the-
and off,
But it dropped naturally in 30 days.
Yeah.
So if you pumped,
you're right.
and it was also dropping naturally, why wouldn't it happen more quickly?
Well, it would help it more quickly, absolutely. But you're gonna have to make a judgment call of how many pumps you're gonna put out here and where you need to put them. And so you're gonna have to prioritize that. Personally, I don't think just putting them around the edges is helping you that much. Because the thickest floodwater is in the middle of the island because of the mound of groundwater that's beneath that. And so you have to do a mass removal. You have to get it from the center of the island to the edges. And so you have to identify where those critical points are, where the transformers are, where the, for lack of a better metaphor, the basements are. And you have to identify and focus on those 2 billion gallons. Wow.
Yeah, I think we're forgetting the volume of that. That's a huge volume of water. I don't know that anything can pump that off in any quick
I wanted
way.
you guys to see the way that works naturally.
That was very
But
helpful.
your point is absolutely right. We have to focus on the highest risk, the most critical points, public works, transformers, public safety. It's built on one of the higher points, and not the reason. Have to focus on that. But there's no way to stick one pump in the ground and suck it all out.
Yeah.
It doesn't work.
So if I could paraphrase maybe, so
Please.
we need to think, we should think very carefully about putting more money into a lot of pumps, given the benefit that we would get, unless we've identified there's certain, we don't have enough for certain strategic areas, for example, but,
You need to figure out what those strategic areas
Yeah.
are.
and your model should kind of tell us, right? Well, not the strategic area, but where the most flooding, I mean,
Yes,
Right.
you're exactly right.
Yes.
Because what we can do is once you identify where those strategic areas are, we can simulate them.
Right.
You have this in your toolbox. We
Yeah.
can simulate how to rapidly get that water out. of you.
Yeah.
And we can simulate that based on the pump performance, 3,000, 3,500, 5,000 gallons a minute. But the aquifer has to yield it because what we're just talking about, so we have to be in an area that will actually get that water. Because if the aquifer itself will only yield 1,000 gallons per minute because of fine grained sand versus coarse grained sand. I don't care what size pump you put in there, it only yield 1,000 gallons a minute, that's all you get. Now, we're doing such high volume because we can drop them in the ponds around the edges. You don't have any ponds in the middle because that water is now trapped and moving through the sand. You have to suck it out of the sand first. Or radius of influence or drawdown curve. Yes, sir.
In that last storm, we had to wait for water to migrate underneath the surface, from one point to another.
That's exactly what we're talking about here.
Right.
100%.
Right.
Peter, Rex.
I'm sorry.
I know this is unusual, but I wonder if I could ask a question since I chaired the Hurricane Task Force.
Go ahead.
So I'd like to return to Scott's point here because the other way is gravity outflow. And what is the capacity of a 36 or 48 inch gravity outfall? Into Bald Creek, that's the one that exists. And then we opened one during Hurricane Florence on South Beach. That it was a massive rate of outflow of surface water. Water that was above the surface didn't have to percolate through anything. And we have the whole lagoon system that's interconnected that moves water very effectively in the western part of the island if you've got an adequate gravity outflow. So I'm wondering what the capacity of the gravity outflows, the existing one is, and the one on South Beach that was used and that we got emergency permission. I think there was even a dune breach at one time.
That's what did it.
And it made a huge difference in that area to the flooding on top of the surface. And then allowed that to continue to allow water to percolate out that route.
Understood. Gravity's very important. And this is actually simulation of the elevation of those groundwater columns. And so we're talking about 4 to 6 feet above sea level. So as long as you had the direct pathway to mean sea level, it'll go. But once you're in the soil, once you're in the sands, it will go as fast as it will.
So Rex, will remind you, one of the recommendations come out of that task force, the bypass lagoon and the outfall into the creek, there was a 30 or 36-inch pipe under Federal Road, but there were only 24-inch pipes on the club side and the village side of the cart path on 6. So we weren't getting using the full capacity of the big pipe under Federal until just recently. Now, within the past couple of years, we upgraded both sides. Now we're maximizing the flow we're permitted we're at our permits limit in terms of how much we could go through the emergency outfall. Now, maybe we can ask for a permit to do more or bigger.
Yeah, I think the other issue is whether there would be other strategic locations where you could put a gravity outflow that's more permanent. I know that's a permitting problem. But if the alternative is 30 days of flooding with the mold and the billions of dollars, the hundreds of millions at least of damage, if pressure on that front would not be beneficial.
All right, I'm gonna point out one detail. Does everyone know what Jacob's Ridge is? That's the line of sand dunes that is the southernmost line of sand dunes on the island. The island's made of ridges of sand dunes, just like Middle Island. Yes. Jacob's Ridge, because of the sand, because of friction loss, it's here. You'll actually see the highest water elevations are behind Jacob's Ridge. So that tells me Jacob's Ridge is a hindrance. That line of sand dunes is a hindrance. Why? Because of friction loss. It's flowing through that sand, but it's flowing through the sand. So to follow your line of thought, the quickest way would be to get through that sand ridge at mean sea level or just above to induce the hedge you need to get from point A to point B. You see that it's long. You got to get through that sand because that sand dune is acting as a restrictive dam.
At one point, there was a pipe under that dune.
That is correct. Do you know why it was closed?
Infiltration.
We were using Pond 3 as high rate infiltration at the time. That's correct. And that sucker was concrete shut.
So we now use a pump to move the water from behind the dune ridge into the lagoon on 16. But the pipe on the other end of Jacob's Ridge between holes 7 and 8, that pipe is still open and still allows water to flow through to get to the emergency outflow.
If you wanted to use gravity and get rid of as much water as possible, as quickly as possible, especially sheet flow on top where the water table is full, you need to breach that dam through pipes or whatever. And that's an engineering problem. Surveying and engineering problem. You guys know what the fish said when he ran into the concrete wall? Damn it.
The hydrologist joke.
What else can I help you guys with?
Anything else?
Oh, very good, very informative.
Thank you.
Jim, thanks so much.
Well,